Hello, and welcome to this FMSP online revision session. It covers the MEI specification and the module FP2 and looking at the topic of complex numbers. In this session we'll look at some key points to remember and work through a couple of exam questions, but we'll start by checking through the relevant part of the specification. First of all, you need to be familiar with the polar form of a complex number and the definition of modulus and argument. Hopefully you'll remember those from further Pure 1 anyway. You need to be confident in multiplying and dividing complex numbers directly in polar form, remembering that the new modulus is the product of the two moduli and the new argument is the sum of the two arguments. But the big topic for this section is de Moivre's theorem. You need to be able to understand it, and importantly you need to be able to apply it. The two standard applications are in finding multiple angle formulae and in summing suitable series, and we'll look at an example of each of these in an exam question. You also need to be comfortable with this definition and how to use it. The other topic that comes up a lot is complex roots. You need to know that every non-zero complex number has n nth roots, and that these are evenly spaced around the vertices of a regular polygon with n sides. This formula here is useful to remember as well for actually finding those nth roots. You might also be asked to explain why the sum of all the nth roots is 0. So, for example, if we look at the nth roots of unity, then the sum of those is this, and this is a geometric progression, and its sum is 1 minus omega to the n over 1 minus omega. But of course omega to the n is equal to 1. By definition that's what omega is, it's the nth root of 1, and therefore 1 minus omega n is 0. A similar argument applies to roots of other numbers. And you need to be able to apply all of this to the Argand diagram. You need to understand what multiplication looks like. You need to be able to draw the roots on an Argand diagram. And you need to be able to solve any geometric twists that they put at the end of a question. And the important thing here is a good, clear diagram. Make sure you mark on it all the information that you've already worked out in a question and see what you've got. So the modulus of a complex number, make sure that you use b squared and not bj squared. We don't want any subtractions in there. And this is the distance of the point from the origin. The argument is the angle between the line connecting the origin and the point Z and the real axis, and it's important that you make sure that you get this angle into the correct quadrant. A good sketch is always helpful. So I've already said you need to learn e to the j theta equals cos theta plus j sine theta. You don't need to memorise these other two results because they're very easy to work out, and if you need to use them the question will start with show that. But you do need to make sure you are familiar with them. Let's check the first one. We know that e to the j theta is equal to cos theta plus j sine theta, and e to the minus j theta is equal to cos of minus theta plus j sine of minus theta, and cos of minus theta of course is cos of theta, and j of minus theta, sorry, sine of minus theta is minus sine of theta. If we add these together we get e to the j theta plus e to the minus j theta being equal to 2 lots of cos theta, and therefore cos theta is equal to e to the j theta plus e to the minus j theta over 2. And the result for sine theta we get by subtracting the two expressions. Here's another one that you need to learn. This is de Moivre's theorem. Exam questions on this are fairly predictable, so make sure you practice doing some. Here's an example. It's a good idea to read through the whole question first and highlight any important points. So first of all, it says use de Moivre's theorem. You have no choice over the method that you use. You must use this or you won't get any marks. Here we're given the form of the final answer, so that's a little bit of a hint, and it's worth looking back when you've finished to check that you've got the correct form. We've got two rather nasty looking sequences there, but it tells you what to do. It says by considering C plus JS. No choice in method again, but also no need to panic about what to do. Just do what they tell you and see what happens. Okay, it says use de Moivre's theorem, so let's start by stating de Moivre's theorem in this particular case. Cos 5 theta plus j sin 5 theta is equal to cos theta plus j sin 5 theta, so it's j sin theta to the power 5. Well, what do you do now? Well, it's always the same thing. The only thing you can do is to expand that by the other method, which is using the binomial expansion. This is absolutely standard for this type of question. So we get cos to the 5 theta plus 5j cos to the 4 theta sin theta plus 10j squared cos cubed theta sin squared theta. Notice that I'm not simplifying my j squareds at this point. I'm going to do that later as a separate activity to make sure that I don't mess up my minus signs. Plus 10j cubed cos squared theta sin cubed theta plus 5j to the 4 cos theta sin to the 4 theta plus j to the 5 sin to the 5 theta. Now let's simplify that. We'll collect the real terms and imaginary terms together at the same time. So cos to the 5 theta, then that j squared is minus 1, so it'll be minus 10 cos cubed theta sin squared theta, and then the other even power is j to the 4, which is 1, so plus 5 cos theta sin to the 4 theta. And then collect my j terms. The first term, 5 cos to the 4 theta sin theta. J cubed is minus j, so we'll have a minus sign there. Minus 10 cos squared theta sin cubed theta. And then j to the 5 is j, so that's going to be positive again, plus sin to the 5 theta. Now, I only need cos 5 theta, so I'm just going to equate the real parts. Sometimes you need to do both. It's worth writing that down so the examiner can see what you're thinking. We get cos 5 theta equals cos to the 5 theta minus 10 cos cubed theta sin squared theta plus 5 cos theta sin to the 4 theta. So I now have an expression for cos of 5 theta, but it's got some signs in it which I don't want. So I need to get rid of those, and to do that I'm going to use the identity sin squared theta equals 1 minus cos squared theta. So every time I've got a sin squared, I'm going to replace that. So cos cubed theta, 1 minus cos squared theta. And sin to the 4 is sin squared squared, so that'll be 1 minus sin squared. Sorry, 1 minus cos squared squared. Now let's multiply this lot out and simplify. Cos to the 5 minus 10 cos cubed plus 10 cos to the 5. Plus 5 cos theta into 1 minus 2 cos squared theta plus cos to the 4 theta. So I've now got 11 cos to the 5 theta there, minus 10 cos cubed theta, plus 5 cos theta, minus 10 cos cubed theta, plus another 5 cos to the 5 theta. Collecting all that together gives me 16 cos to the 5 theta, minus 20 cos cubed theta, plus 5 cos theta. And therefore we were asked to find A, B and C, so it's a good idea to write those down. Therefore A equals 16, B equals minus 20, and C equals 5. Now let's have a look at part B, which is summing series. It says by considering the sum of those. So we're going to add those together, and the usual thing to do is to put your coses and your j signs together and see what it looks like. So C plus JS equals cos theta plus j sine theta plus cos theta plus 4 pi over n plus j sine, 2 pi over n, the first one, theta plus 2 pi over n plus cos theta plus 4 pi over n plus j sine theta plus 4 pi over n plus dot 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 plus cos theta plus 2n minus 2 pi over n plus j sine theta plus 2n minus 2 pi over n. Now each of those can be written in the exponential form. Cos theta plus j sine theta is e to the j theta, and then e to the j theta plus 2 pi over n plus e to the j theta plus 4 pi over n plus dot 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 plus e to the j theta plus 2n minus 2 over n pi. Hopefully you'll recognise that this is a GP. The first term A is e to the j theta, and the common ratio R is e to the j 2 pi over n. So we use the standard formula for the sum of a GP, which of course is in the formula book, a 1 minus r to the n over 1 minus r. And substituting in my values, a was e to the j theta, 1 minus r is e to the 2j theta pi over n, and that is to the power n, all over 1 minus e to the 2j pi over n. Simplifying that, I get 1 minus e to the 2j pi and of course e to the 2j pi is equal to 1. So I've got e to the j theta 1 minus 1 all over that. So I'll just put, because this is a show that question, since e to the 2j pi equals 1, and that equals 0. Now if c plus js is 0 overall, that means that the real and the imaginary parts must both be 0. and therefore C is 0 and J is 0 as required. Well, that's the end of that question. Let's go back and have a look how the mark scheme is applied to this question. For part A, there is a method mark for using Moi's theorem. There's another method mark for using the binomial theorem appropriately, and there's an accuracy mark for getting the correct real part. You don't need the imaginary part, so they're not going to be too worried about that. There's then a method mark for equating the real parts. There's a method mark for using sine squared theta equals 1 minus cos squared theta. And there's an accuracy mark for getting down to the end with the correct values for A, B and C. For part B, there's a method mark and an accuracy mark for getting C plus JS into the exponential form. There's then a method mark for attempting to sum, and accuracy marks for A and R used correctly, but noting that J must be seen in this. There's then another accuracy mark for actually managing to get everything in and correct. If you get all 5 marks, and this is dependent on the previous 5 marks, there's then an explanation mark for a convincing argument about why that comes out to be 0, and another explanation mark which is dependent on the previous one as well as the other 5 for concluding that C and J are both 0. Okay, let's have a look at another exam question. This one includes something on roots and a slightly different style of application of Moi's theorem, less explicitly. So again, read through the whole question first. So we're given that z is cos theta plus j sine theta. We've got to get z to the n and z to the minus n. It says in simplified trig form, so we need to make sure we simplify. By considering, so no other method, we've got to make sure that we use that method, and it's a show that question. We're given the answer, so we need to make sure that our working is clear and that we've done at least 3 marks worth of working. We've then got to obtain an expression for cos to the 6th theta minus sine to the 6th theta, so we'll have cos to the 6th. We'll need to do something with sine to the 6th. We've got to make sure that it's only in terms of those functions. And then we've got a complex roots question. We're looking at a square root and a cube root, and we're told that these 2 points both lie in the 3rd quadrant. We must make sure that not only do we find Z1 and Z2 in the required format, but that we don't forget to draw the diagram, and that we've got all 3 points on it. And we've got to find a product and determine the quadrant of the Argand diagram in which it lies. So again, 2 bits to do for each of those questions. Make sure that you do both of them. Okay, so there's only 2 marks for these, so they're probably just 1 straight mark each, but make sure we put enough working in to get them right. So z to the n plus z to the minus n. Z to the n is cos n theta plus j sine n theta, and cos to the z to the minus n is cos of n theta minus j sine n theta. Noting this is only worth 1 mark, we don't really need to do any more working than that. We get 2 cos n theta. Z to the n minus z to the minus n is cos n theta plus j sine n theta minus cos n theta minus j sine n theta. And that comes out as 2j sine n theta. By considering, so let's start with that. Z plus z to the minus 1 to the power 6 and expand using the binomial. So z to the 6 plus 6 z to the 5 z to the minus 1. You can cancel these on your first line of working, but it might be safer not to, and then you can check that you've done your binomial correctly and do the cancelling later. 15z squared z to the minus 4, 6z z to the minus 5, and z to the minus 6. So simplifying, z to the 6 plus 6z to the 4 plus 15z squared plus 20 plus 15z to the minus 2 plus 6z to the minus 4 plus z to the minus 6. Now then, I need cos to the 6, and of course I've just worked out that z to the n plus z to the minus n is 2 cos n theta. So in the case z equals 1, I get 2 cos theta all to the power 6. And let's group these together. So z to the 6 plus z to the minus 6 plus 6z to the 4 plus z to the minus 4 plus 15z squared plus z to the minus 2 plus 20. The left hand side is 64 cos to the 6 theta, and z to the 6 plus z to the minus 6 using our previous result is 2 cos 6 theta, and then 12 cos 4 theta and 30 cos 2 theta plus 20. And dividing both sides by 64, I should get the given result. That's 2 64ths is 1 32nd. 12 64ths is 6 32nds. 30 64ths is 15 32nds. And 20 64ths is 10 32nds. So that does come out correct. Now I need to do the same thing with sine. So I can say similarly, z minus 1 to the minus 1 all to the 6th. And the only thing I've got to change here are some minus signs, so I can do that in one line of working. From my previous result. And using the result in part A, that's 2j sine theta all to the power 6, and pairing things up, z to the 6 plus z to the minus 6 minus 6 lots of z to the 4 plus z to the minus 4 plus 15 lots of z squared plus z to the minus 2 minus 20. And that gives me 64j to the 6 sine to the 6 theta is 2 cos 6 theta minus 12 cos 4 theta plus 30 cos 2 theta minus 20. And j to the 6 is minus 1, so dividing both sides by minus 64 gives me sine to the 6 theta is 1/32 minus 2 cos 6 theta plus 6 cos 4 theta minus 15 cos 2 theta plus 10. So now I can get my previous expression for cos to the 6 and subtract this expression for sine to the 6 and get 1/32, and I had 2 cos 6 theta, take away minus 2 cos 6 theta gives me it shouldn't be a 2 there, that should be a 1. I've got cos 6 theta minus cos 6 theta gives me 2 cos 6 theta. And 6 cos to the 4 minus 6 cos to the 4 is nothing. And 15 cos 2 theta minus 15 cos 2 theta is 30 cos 2 theta. And 10 minus 10 is nothing. So I can then simplify that, taking out a factor of 2, giving me 1/16 cos 6 theta plus 15 cos 2 theta. Part B is about roots. I've got a complex number w is 8e to the j pi over 3. Z1 is a square root. So the square root of 8 e to the j pi over 6, but that's not in the third quadrant. So it's a square root, so the other one will be on the opposite side, so I need to add pi. And I can simplify that, that's 2 root 2 e to the j 7 pi over 6. Z2 is a cube root. The cube root of 8 is 2, and I need to divide my argument by 3. But again, pi over 9 is not in the third quadrant. It's sort of about here, and to get all the way around to the third quadrant, I'm actually going to need to add 2 lots of 2 pi over 3. So that comes out to be 2e to the 13 pi over 9. Okay, now I need to draw these on an Argand diagram. So pi over 3 is about 60 degrees and a modulus of 8, so we'll do that there. Use a ruler on your diagram. Label it clearly as W. Z1, an angle of 7 pi over 6, is going to be quite a bit smaller in modulus and round there. And Z2 will have a smaller modulus again and down there. And the final part of this question, finding the product Z1, Z2. So this is looking at multiplying in polar form. I've got 2 root 2 e to the j 7 pi over 6 times 2 e to the j 13 pi over 9. So I need to multiply those moduli, so that's 2 times 2 root 2 e to the j 7 pi over 6 and add the arguments. Now you should be able to do these in your head, but you don't need to worry because you've got a calculator in the exam, and we get 4 root 2 e to the j 11 pi over 18. And that is a little bit over pi by 2, so that lies in the second quadrant. So let's go back and have a look at how the mark scheme is applied to this question. For part A, part 1, it's just 2 marks and they are B marks, so you just need to get that right. It's worth putting some working in to make sure you get them right, but the credit is just for the answers. For part 2, you get 1 method mark for expanding z plus z to the 1 to the power 6 using the binomial. You get another method mark for using the previous result in one of those cases where n is 2, 4 or 6, just using that previous result somewhere. And the final accuracy mark for following through with correct working to the end. Notice that that answer is given so that the accuracy mark is for all the working being correct. For part 3, there is just an answer mark, B1, for translating your working from part 2 into the slightly different one with z minus z to the minus 1. There's a method mark then and an accuracy mark for getting your expression to this stage. There's then a method mark for attempting to subtract and an accuracy mark for getting an expression in terms of cos 2 theta and cos 6 theta. For part B, there is a method mark and an accuracy mark for each of the roots. The method mark is for correctly manipulating the modulus and argument, and the accuracy mark is for getting the right one. So the method mark is for rooting the modulus and dividing the argument, and then the accuracy mark for making sure you've got the right one in the correct quadrant. For the diagram, you get 1 mark for the modulus of each of those being reasonably accurate, and a graph mark for the arguments being reasonable. In other words, them being in the right quadrant and fairly close to the right angles. You're not expected to measure them, you're expected to do it by eye, but they do have to be reasonable. And there's a special case, which is that if you get if you get 2 of them, but you don't get the third one correct, but those 2 are both okay, then they'll give you G1, G0. So if 2 are right good points. Okay, for part 2 of part B, 1 method mark for multiplying the moduli and adding the arguments, an accuracy mark for an answer in any equivalent form, and an accuracy mark for correctly spotting that that lies in the second quadrant. At which point I spot that I skipped a line of working. That comes out to be for root 2 e to the j 47 pi over 18, which of course is over 2 pi, so if you take off 2 pi you then get 4 root 2 j e to the j 11 pi over 18. Well, that's all you need to know for complex numbers. I look forward to your company in some of the other FP2 revision videos and wish you all the best for the exam. Goodbye.